Yeah, let's begin. Hello, everyone. Today we'll be discussing graph neural networks or GNNs, which is a powerful deep learning approach for working with graph structured data. And by the end of this recitation, we'll also be diving deep into, we'll also be exploring how GNNs can be implemented. We'll start with covering some key applications of GNNs and then deep dive into their implementation details. But before we begin, I also wanted to mention that we have released Lab 8, which will be covering Hugging Face and how to use pre-trained models and datasets from the Hugging Face library. So I encourage you all to watch that lab as well. So now let's start beginning with exploring some real-world applications of GNN. Companies like Facebook use GNNs to understand the complex web of social connections, which helps them recommend friends and suggest relevant content to users based on social graphs. Also, we can also see, as in the image here, GNNs are used to predict the potency of potential drugs by graphically modeling the interaction between atoms and molecules. They're also used in discovery of new antibiotics. Streaming platforms like Netflix also leverages GNNs to recommend movies or shows based on viewing patterns of users. And in the field of medicines, GNNs are widely used to predict disease progression by modeling patient health records as a graph, where each node represents a patient and edges represent medical events. So now if we go back to the previous slide for a second. Yeah. So over here, we can also deep dive into the structure of these graphs. So in the context of GNNs, the nodes represent atoms and the edges represent bond between these atoms. So each of these nodes and edges come with their own set of features. Node features can include the atom type, the number of protons, and charge, whereas the edge features can represent the bond type. By understanding these features, GNNs can learn to make accurate predictions about the system being modeled. In the following slides, we'll explore this concept more in detail. So now, for this slide, we can take the example of where we have a molecule which has been represented as a graph. And now we're going to train a graph neural network to perform tasks, say a binary task, which is to predict whether a mole will inhibit a given bacteria. For this, we start with a curated data set of molecules with known outcomes, that is, whether it will inhibit E. coli or not. And then we start training this GNN with the training data. Once we have trained the GNN, we can use to evaluate a set of candidate molecules, say roughly about top 100 candidates. And then after we select these 100 molecules, we will thoroughly investigate this by chemists. Now let's also look at a real-world example of the application of AI and GNNs. In 2020, the researchers at MIT used a deep learning algorithm to identify a new antibiotic compound called as halicin. This drug was found to kill many strains of bacteria and prevented the development of antibiotic resistance in E. coli. You can read more about this interesting research in the link given in the speaker notes of the slide. Now, let's also see what you can do with graph data. So GNNs can address different types of machine learning problems using graph data. To begin with, we can do node level predictions. So here we predict attributes or classify unlabeled nodes in a graph by leveraging information from neighboring nodes. For example, predicting if a person smokes or not based on their social network. Second, link level predictions. In this, we predict the existence of nodes, edges, or links between nodes. So a common use case is recommending the next product, or a customer might be interested in purchasing based on their purchase history. So this is very well used in the recommender systems. Third is graph level predictions. Where here we make predictions at the graph level, such as classifying an entire molecule as a potent drug or not.
Okay, thank you, Hine. So I'm going to continue on how we actually want to train this model. So in order to proceed, let's revisit the concept of embeddings a little bit. So in natural language process, in NLP task, I think we have various ways in which we can represent embedding. So in one of the most popular representations is using the one-hot encoding, which means that we would basically represent maybe a one or a zero in the case of banana. So we would consider our whole vocabulary, which would be all possible words in the English dictionary if we're dealing with English. And then where we have banana, then we are going to represent a one, and for all other spots, it's going to be zero. But we also have other representations, like the distributed representations, which we are not representing one or zero, but we are representing some values restricted on some dimension d. So d is the size of our embedding vector, and for each of the positions, let's say from 1 to 512, then we have some value which gives us a vector representing banana. And in the same case, we can have a look at the graph as a node containing various features, and these features can be represented using some form of embedding. So for every node in the graph neural network, our task is to move from some input embedding, let's say x1, x2, and get some other embedding, which is like h1, h2, h3, which indicates how a node interacts with its neighbors. But we can simplify this much further by using a vectorized notation, which means that in this vectorized notation, similar to the way we represented our embeddings in NLP, in NLP task, we can also represent each node with some embeddings, and we form something which we call node embeddings. And of course, our GNN right now, the task will be to output the same connections, but with some updated embeddings. And in order to work with graphical neural networks, it's important to understand how the model is trained, or how the weights are updated. And so far the most promising approach, which resembles the convolutions like we have in CNN, is what is known as message parsing. So in message passing, we have like several stages. And the first stage is we want to aggregate all our messages to a target node. So here, all the nodes, they have some messages which is represented by their embedding, and then we want to pass it onto our target node. And at the end, we want our target node H1 to have some representation which comes from all the neighboring nodes around it. So in the first step, we aggregate the messages to it, then we update it. And we're going to see the update rule in the next slide. So first, as I already mentioned, so we aggregate the messages to our target node, which means that all the neighboring nodes, they're going to do some form of passing some messages. And then after we get the messages from all the neighbors, then we're going to do some update step, which means that we're going to update the messages of the current node, and the current node using its current message, its current embeddings, and those that are gotten from its neighboring nodes. And if we repeat this process over and over, then we can see that it's just like it's almost similar to a convolution, where in each layer we are doing some sort of message passing, which is like the aggregate and update of the target node's embeddings. So, and here, if we are revisiting the input and output, so our input, it's a matrix X, which represents the embeddings of all the nodes, and we have an adjacency list, adjacency matrix, which also represents how the nodes are connected. And then we want to output H, which is also another matrix, which contains the final embeddings for all the nodes, and A remains the same, which is how the nodes in the graph are connected. And after doing this, then once we reach this final representation, we can perform various kinds of tasks like Hina mentioned above. So we can perform like some node classification using maybe just the embeddings of HI, let's say if it's H1. So we can do some node level classification, or we can do some link level classification, trying to determine what are the representations between this node and another node, or we can do a whole graph level classification considering all the nodes and all the links in the whole node embedding space to do some form of classification. So going back to the message passing algorithm, how it operates. So let's say we have some target node, which is node 1, and we want to learn the representations, the node embeddings of node 1. Okay, so in the first stage of our message passing algorithm, we want to aggregate all the information. So as we can see here, the node 5 is not included because node 5 is not in the immediate neighborhood of node 1. So we would aggregate all the messages from in the neighborhood of node 1 and then pass the information to the target node. And the second thing is to do the update, which we would update each node's features based on the message to form an embedded representation. And more mathematically, we can see the next stage, k plus 1, as an update using HU, which is the current state, plus the aggregated messages from every node. And we can, of course, represent this mathematically as using some weights. And this weight is just to tell us how much important those messages or coming from every node is going to matter. And of course, we also have some activation to introduce non-linearity. However, there is a more compact version which we can deal with using shared parameters the same way we deal with GNNs by using shared filters across different dimensionality by combining W, the self weight, which is the weights on how much embeddings, how much current embeddings, how much value we should pay, how much attention we should pay to the current node embeddings of our target node, and also that of the neighboring. So in order to do this, then we can represent, we combine the W self and W neighbor, the weights of the self and the weights of the neighbor to form one weight matrix, and introduce this A, which is the adjacency list, plus I, which is the identity matrix, to do something which we call self loops. And this self loop is basically going to account for W self HU in this same representation. But this method is found to be more efficient while training, because with shared parameters, then we have less parameters to train, and hence in each step, then our updates become more meaningful. And then, yeah, so that's it. So there are various propositions which have been proposed by various researchers in the whole graph neural networks using a convolution perspective. And I think on Monday we saw it in class, and it's also included in our slides. So right now I'll pass it on to Dennis to walk us through one of the implementations of graphical neural networks. Okay, Dennis, maybe you can share your screen.
Yeah. Share. Give me a few minutes to share my screen. Oh, can you see my screen?
Yes.
Okay. Sorry about that. Let me just... Yeah. So I'm going to show the practical side of graphical neural networks as we've just seen in the theory. So in this notebook, we shall be showing two tasks, that is node classification and graph classification. So like Gabriel had explained earlier, node classification covers the individual nodes that exist within the graph itself, whereas graph classification looks at the entire graph and tries to assign a label to the entire graph instead of individual nodes. And we saw earlier the applications of each of these tasks. So here we shall start with node classification, but before that, we need to install some packages. So as usual, we shall import Torch, and in this particular task, we are going to use PyTorch geometry, which is the library that's used for graphical neural networks inside PyTorch. We shall be using matplotlib to visualize the plots and see the results of our classification task. So here first, so we're going to look at a graph. So the dataset that we have here is one that uses papers, so it's sort of a citation network. So to read through this, so to demonstrate, we're going to use the Cora dataset, which is a citation network, where nodes represent documents, and each node is described by a 1433 dimensional bag of words feature vector. And two documents are connected if there exists a citation link between them. The task is to infer the category of each document, and we have 7 categories in total. So here, we have a graph. So each document will be represented by a graph, and um, each document is represented by a node, and at that node, we have a vector of 1433. So that vector contains, I don't know whether bag of word representation, which is like which is a representation normally used in NLP to represent documents. So it can be like word frequency or inverse TF IDF. So to go in depth, we shall first load the dataset itself from Torch geometry datasets inside Planetoid. And then we shall use the normalized features. So we have a transform called normalized features here. Then, so we load the dataset using this line and normalize the features. Then now we shall look at some information related to the dataset itself. So we shall count the number of graphs inside the dataset, see the number of features for each node inside the graph. We shall look at the number of classes that exist within this dataset. Then we shall look at a sample from the dataset. So to gather the statistics, so here we have number of nodes, which is we can get by using the number of nodes feature. Then we have number of edges, which you can get from the edges. Then here we include, so in the dataset, we have a mask. So the purpose of the mask is to differentiate between the training dataset and the test dataset. So what they do is they mask out elements of the graph that are reserved for classification and leave some for training. So here we can, using the properties of this graph, we can see, so here we have train data.train mask. So this will show us the number of samples that are left for training and the number of samples that are left for testing. Then we have the degree, which will be the number of edges divided by the number of nodes. But that's on average, since different nodes have different number of edges connected to them. Then we also check whether the graph has any isolated nodes. Those are nodes that are not connected to any other node inside the graph. Then we check for self loops and also check whether the graph is undirected. So here we can see from the results that we have an average node degree of 3.9. So on average, each node is connected to around 4 other nodes. Then we're using 140 nodes for training out of 150 nodes. So then we have so we have a training node label rate of 0.05, which is like 5%. 5% of the nodes are being used for training, whereas the rest are reserved for testing. Then we see it has no isolated nodes and there are no self loops, and it's undirected. So moving on, so here this markdown cell provides the summary of the information stated in above. So we shall move ahead by training an MLP. So for these graph neural network tasks, such as node classification, we can easily use an ordinary MLP to perform the task, but as we shall see that the performance of graphical neural network will be much better than that obtained from the MLP. So to use the MLP, we shall use the normal functions. So we shall have a linear layer, and that linear layer takes in the number of features. That's each feature for, remember we had features from each node, which was 1,433. Then we shall convert them to a particular hidden size, which is like hidden channels. Then finally, we shall output the number of classes, which is 7. So here we have our forward method, and uh, we pass the input sequentially through all the layers before obtaining the output. So here we create our model and then print the model. As you can see, the summary of the model, we just have 2 linear layers with ReLU activation and some dropout. Then from there, we're going to train our network, our MLP, using cross-entropy loss and Adam optimizer. So we're going to write 2 functions, a train and test function, which follows the normal procedure we have been using for all our deep learning models. We set the model into training mode, clear the gradients, then pass the data through the model, then calculate the loss. So here we only want to calculate the loss for the train nodes. So we apply a mask to our outputs of the data. So that's why here you can see that we have output, but we mask it using the train mask, and also for the labels we mask them using the train mask. Then we perform back propagation and then take an optimization step. Same thing for the test set, except that here we don't need to do back propagation. We're going to run this for around 200 epochs and see the loss after this. So I've already run the model. At the end of training, you can see that at the end of 200 epochs, we have a loss of 0.3810, but on checking the accuracy of the model, we can see that it's only 59%. So here, the poor performance of this model can be attributed to factors such as overfitting, since we have a very small training set compared to the overall data set. So like you saw earlier, we have only using 5% of the data for training and the rest for testing. So that results in model overfitting. And the other thing is it's not incorporating information from the neighboring nodes. So it's just looking at the node itself and only using the information inside the node. But then we shall see if when we apply a graphical neural network which considers information from the neighboring nodes, shall see that the performance of the model will improve. So here we shall be using a graphical convolution network, as Gabriela had explained earlier, which is which is described by this equation given here. Whereas you can see that the MLP only performs linear transformation of the data. So to apply a graphical convolution network, we shall build our model using the following. So we have a convolution layer, which takes in the number of features and the number of hidden layers. So building the model is very similar to what we had for the MLP, except that in the forward, we shall also pass in the information, the edge information, which shows like which node is connected to which other node. So here we pass the information through, so we shall have our input, which goes through the first graphical convolution network layer. We pass in the edge information, then apply the ReLU activation function, followed by dropout, and then pass the information again through the second layer. So this is here is the summary of our network. So we are going to visualize the data, okay, the features of our model just before training the model. And as you can see here, you'll see that in the graph, the labels are all over. There's such a mix between of the nodes. So you can't clearly separate out which nodes belong to which class. But as we shall see later, after training the model, there will be a clear separation between each of the classes. So from there, we have our normal procedure for training and testing the model as we had seen earlier. Nothing really changes. So we are going to train our model for about 100 epochs and test it to see its performance. So after 100 epochs, you can see that the loss goes down to 0.5799, which is higher than what we had for the MLPs. But when it comes to the classification accuracy, we see that this model achieves 81.5% accuracy, which is way higher than the 59% accuracy where we had attained using the MLP. So this clearly shows you that graphical convolution networks are a superior method to MLPs when it comes to node classification. And when we plot out our classes after training, we can see that there is sort of a separation between the seven labels that we had in our data set. So you can see here we have green, though it's tainted with some spots of purple. We can sort of see a clear separation, at least more separable than we initially had. And this is as a result of using the graph network. Then now we can then move on to graph classification. So previously node classification were classifying each individual node in the graph. But when it comes to graph classification, we are going to give the entire graph one label. So here for this, we are going to use a molecular data set. So here, like you can see in this file, it's written, the most common task for graph classification is molecular property prediction, in which molecules are represented as graphs, and the task may be to infer whether a molecule inhibits HIV virus replication or not. So here they say that the TU Dortmund University has collected a wide range of different graph classification datasets known as the TUD datasets, which are also accessible via the plot geometry datasets class. So we're going to load the data like we're done for node classification and check out its properties. So here we load the dataset using this line from the TUD dataset. So we can check for the number of graphs, the number of features, so the number of features, that's how many features does each node have. Then we look at the number of classes. So here, since we're just determining whether a molecule inhibits HIV or not, it will be a binary classification task. So we just have two classes. Then we can look at an individual graph within the data set. So considering the individual graph, we can look at the number of nodes, the number of edges, the average node degree. We look at whether it has any isolated nodes, whether there are any self loops, and whether the graph is undirected or not. So in this output, we can see that in our data set, we have 188 graphs, each with so each node in the graph has 7 features, and we have only 2 classes. So here, this information also provides so we have date age index information. Also, we have age attribute as well as the classification of the label, which is Y. So by inspecting the first graph object of the dataset, we can see that it contains 17 nodes. So here we shows you the X 17 nodes, and remember each node has 7 features, 38 edges. So we have 38 edges leading to an average node degree of 2.24. So remember here we said that the graph was undirected, so that's why we have 2 by 38. It also comes with exactly 1 graph label. So so each graph is labeled with whether it inhibits HIV or not. And in addition to previous datasets, provides additional 4-dimensional edge features. So we have edge attributes here, but for this example, we are not going to use them. So an example of an edge attribute could be like how strong a bond is between 2 atoms inside the molecule. So that's the kind of information that's captured by the edge features. But for this example, we shall not be using that edge information. So then we can see that Python geometry provides some useful utilities for working with graph datasets. So we can shuffle the datasets and use the first 150 graphs as training graphs while we use the remaining for testing. So like, it's very important in machine learning to shuffle your data before you use it for training. Otherwise, you could experience challenges like it was explained in class. So so for graphs, we shall use a different kind of batching. So the ordinary batching that's used for images or words may not apply. So in words, we usually pad the sequences so that the lengths match, the lengths of the sequences inside a single batch match. Or for computer vision, so for images, we try to resize all the images within a batch to have the same size. So that makes it easier to batch them along an additional dimension. But for graphs, this would be very wasteful. And so this library introduced a new method of batching. So like can read through, says Pareto geometry opts for another approach to achieve parallelization across a number of examples. So here, adjacency matrices are stacked in a diagonal fashion, creating a giant graph that holds multiple isolated graphs, and node and target features are simply concatenated in the node dimension. So here, like you can see, the graphs are stacked in a diagonal form. So you can see graph A1 and A2, whereas the other information is stacked like you can see vertically. So this is done automatically by using the data loader from the touch geometry library. So we are using a batch size of 64 and shuffling. Remember we have to shuffle our training data set, whereas for the test data set, we don't have to shuffle it. So here we can see that we can look through our data set, our data loader, and see that the first batch has 64, the second batch as well as 64, but last batch has 22 since there are not enough samples to include there. So, but when we look at each of the individual batches, so we can see that, for instance, our X information, which is like the nodes, we now have 1,188 nodes, which is a combination of the 64 graphs. Then for edges, we have 2,636. But since you need undirected, it's an undirected graph. You have two dimensions here. Then we have 64 labels. We have edge attributes, which is 2,636 because each edge is represented by a vector of dimension 4. So from there, so you can see the features of the first batch, the second, and the third batch. So then Okay, there is also another piece of information, which is the batch. So the batch tells us where the node, where each node belongs, to which graph each node belongs. That's the information that can be found in the batch. So here we're going to train a graphical neural network. So the process of training the network is we embed each node by performing multiple rounds of message passing, like Gabriel had explained earlier. Then we aggregate node embeddings into a unified graph embedding. That's the readout layer, and train a final classifier on the graph embedding. So there exists multiple readout layers in literature, but the most common is simply take the average of the node embeddings, like it's shown here. So PyTorch provides functionality, that's the global mean pooling, so which takes the node embeddings of all nodes in the mini batch and the assignment vector batch to compute a graph embedding of batch size by hidden channels for each graph in the batch. So the final architecture for applying GNNs to the task of graph classification then looks as follows. So here you shall see we are using the same layers. So we have, in this case, we have 3 layers, conv1, conv2, and conv3. So here we shall pass in the number of node features, which was 7, then have hidden channels. So we shall pass it through 2 other layers. Then finally, we shall have our linear layer, which will perform the classification at the end. So in this case, we pass in our forward method, uh, we have to pass in the edge index information as well, since we're using a graph convolution network. So we pass in through the first convolution, then apply activation, then followed by this the readout layer, which performs the pooling. Then before applying the classifier, we perform dropout, which helps with regularization of the network, then use our linear layer. So this is a summary of the network that we have built. Then we follow that by training the network. So the training procedure doesn't differ from what we've seen earlier. It's just pass the data through the model, calculate the loss, perform back propagation, uh, then zero out, clear the gradients. Then the testing also follows a similar procedure, except that we don't have back propagation there. So then we're going to train our network for around 171 epochs and see the accuracy. So here we can see that the accuracy at the end of training is 76%. So here they go ahead to explain that the reason for fluctuation in accuracy can be explained uh, by the rather small data set, only 38 test graphs, and usually disappears once applied to a larger data set. I think that's all we had today for graphical convolution networks. Are there any questions?